For our final project, we're going to be discussing Chapter 13, Non-Parametric Tests. And our project is created by Cassie Miller, Jennifer Flynn-Orrell, and me, Patrick Bishop. So let's start a little bit before we talk about non-parametric tests, talking about what parametric tests are. Parametric tests are statistics tests for population parameters such as means, variances, and proportions that involve assumptions about the population from which the samples were selected. ZT and F tests are examples of parametric tests. Now, what are those assumptions that we might be making when you want to use a parametric test? Well, the biggest one is that the populations are normally distributed. So what do you do if a population is not normally distributed? Which takes us, of course, to non-parametric tests. Non-parametric tests are used to test hypotheses that do not involve specific population parameters such as sigma, mu, or p. Some advantages of non-parametric tests are they can be used to test population parameters when the variable is not normally distributed, of course, like we just said. They can be used when the data are nominal or ordinal. They can be used to test hypotheses that do not involve population parameters. In some cases, the computations are easier than those for their parametric counterparts, and my favorite, they are easy to understand. Some disadvantages, however, are that they are less sensitive than their parametric counterparts when the assumptions of the parametric methods are met, which means that larger differences are needed before the null hypothesis can be rejected. They tend to use less information than the parametric tests, and they are less efficient than parametric tests when the assumptions of the parametric methods are met, which means that larger sample sizes are needed to overcome that loss of information. Some final notes about the chapter. Many non-parametric tests involve the ranking of data, which is the positioning of a data value in a data array according to some rating scale. And it's important to remember that ranking is an ordinal variable. And of course, our work cited all the information that we're going to present to you today, and this introduction has come from Alan Blumen's the Chapter 13 Non-Parametric Statistics in our Elementary Stats, a Step-by-Step Approach 8th edition by McGraw-Hill. Thank you, and we hope you learned a lot today.
We're going to be talking about the single sample sign test. This is the simplest non-parametric test. It's used to test the value of a median for a specific value. The procedure: you hypothesize a specific value for the median of a population. Then you select a sample of data and compare each value with the conjectured median. If the data value is greater than the median, it equals a positive sign. If the data value is less than the median, it equals a negative sign. And if the data value is equal to the median, it equals 0. You count the number of positive, negative, and zeros you have for the sample. If the null hypothesis is true, the number of plus signs should be approximately equal to the number of minus signs. If the null hypothesis is not true, there is a disproportionate number of plus or minus signs. The test value is the smaller number of plus or minus signs. When sample size n is less than or equal to 25, you use Table J in Appendix C to find the critical value. For a specific alpha, if the test value is less than or equal to the critical value obtained from the table, the null hypothesis should be rejected. When the sample size is 26 or greater, the normal approximation can be used to find the test value. The critical value is found in Table E in Appendix C. This formula will be used. X is the smaller number of positive or negative signs, and n is the sample value. The next test is the paired sample sign test. This test is used to test sample means in a comparison of two dependent samples, such as before and after test. To find the critical values, you subtract the after values from the before values and indicate the difference with a positive or negative or 0 according to the value. Use table J, and the n is equal to the total number of positive and negative signs. Here is an overview of the procedures for both the single sample and the paired sample test. Okay, I'm using sample exercise 13-2, number 7. And the question reads, cyber school enrollment. An educator hypothesizes that the median of the number of students enrolled in cyber school in school districts in southwestern Pennsylvania is 25. At alpha equals 0.05, is there enough evidence to reject the educator's claim? The data are shown here. What benefit would this information provide to the school board of a local school district? Okay, so here the median, the projected median is 25. So your null hypothesis is 25, and that's your claim. And then the median does not equal 25. Okay, good. I'm sorry. This is an example for a single sample sign test. I'm using exercise 13-2, question number 7. The question reads, cyber school enrollment. An educator hypothesizes that the median of the number of students enrolled in cyber schools in school districts in southwestern Pennsylvania is 25. At alpha equals 0.05, is there enough evidence to reject the educator's claim? And here, so you have your null hypothesis is the median number is 25, and that's our claim. And then we have our alternative hypothesis that the median does not equal 25. Here is our data sample here, and the first step is to go through and give it either negative or positive, determining if it's greater than 25, it has a positive. If it's greater than or equal to, there's a positive number. If it's less than, then it gets a negative number. If it's equal to, it gets a 0. So I went through and labeled all of them. And then we're using alpha is 0.05. The n is equal to 19. This number comes from the positive and negative from your sample. The critical value is 4. Test value is 7. Therefore, the test value is greater than your critical value. So you do not reject the null hypothesis. There is not enough evidence to reject the claim that the median number of students enrolled in cyber schools in school districts is 25.
Sign tests don't consider the magnitude of the data. And so when you need to consider the magnitude of the data, use one of the Wilcoxon tests, because they do consider the differences in magnitude by using ranks. And even though both Wilcoxon tests are used for distribution comparisons, you use the Wilcoxon rank sum test when the samples are independent. And these are the formulas used to calculate using the Wilcoxon rank sum test. R equals the sum of the ranks of the smaller sample size. The smaller sample size is indicated by the variable n sub 1. N sub 1 is the smaller of the sample sizes, like I just said. N sub 2 is the larger of the sample sizes. And it's important to note that both n sub 1 and n sub 2 must be greater than or equal to 10. Also important to note is that if both n sub 1 and n sub 2 are equal sample sizes, then they can be used interchangeably. So if the sample sizes are equal, either of them can be picked for n sub 1. So z equals r minus mu sub r, quantity divided by sigma sub r. Mu sub r equals n1, and then in parentheses n1 plus n2 plus n1, quantity divided by 2. And sigma sub r equals the square root of the quantity n1 times n2, parenthetical n1 plus n2 plus 1, quantity divided by 12. And now we're going to take a look at one of the problems from our text to see how you use the Wilcoxon rank sum test to calculate the value. So there are 5 steps when you're using the Wilcoxon ranked sum test. The first is to state the hypothesis and identify the claim. The second one is to find the critical value, which we'll use the abbreviation CV to represent for the remainder of the exercise. Step 3 is to compute the test value. Step 4 is to make your decision. And step 5 is to summarize the results of your computations. Okay, so what we're going to be working out today is found on page 686 of our text in the box titled Exercises 13-3, and we're working out problem number 4, which asks us to determine from 2 groups, male and female, listing times for prison sentences in months, if, when taking into account that alpha equals 0.05, if there is a difference between the sentence received by each gender. And the claim represented by H sub 0 here is that there is no difference in the sentence received by each gender. So let's see if that works out. So that was step 1, to identify the hypothesis and the null hypothesis and to suss out what the claim is. So we've done that. Step 2 is to look up the critical value, which is plus or minus 1.96, which can be found in the appendix in table E in our text. And step 3 is to actually work out the problem. So what we have to begin by doing is ranking all of our data. So we list in order all of the values in our data from least to greatest, which I've already done here. Secondly, we group them by which group they belong to. F represents females here, M represents males, of course, so I've put a mark above each number of time in months to represent which group it belongs to. And third, and finally, when we make our table here, we have to rank them each, again going from least to greatest. When you get to duplicates, like there are 2 12s here, that comes in position 10 in rank, so you put 10.5 for each of them, and then you skip the 11 and go to 12 for the next value in the table, so that you have, when you end, a number that represents all of the data that you have. We have 26 points of data here, so we end with 26. That's how you know if you've done it right. So, to determine R, we have to sum all of the ranks from our smallest group. Now, males has 12, and females has 14. So we know that N sub 1 and N sub 2 have definite values, but you can't use them interchangeably because they're not the same. So, when we sum all of the values, the rank values for males, we get 191. I went ahead and wrote that down so that I don't make a mistake while we're doing math here. So N sub 1, of course, is a smaller value, which is 12. N sub 2 is 14, like we already said, so we fill in our formulas here. We have N sub 1 is 12, 12 plus 14 plus 1, all divided by 2 equals 162. And we go down here to sigma sub r and put in all of our values again. 12 times 14, 12 plus 14 plus 1, quantity divided by 12, which will give us 378. We take the square root of that, and we get 19 point, a really long decimal that we're going to just round to 2 decimal places, so 0.44. And then we have to fill in everything for z. To find z, r minus sigma sub r, which is 191 minus 162, quantity divided by, or I'm sorry, mu sub r, quantity divided by sigma sub r, which again is the square root that we found a minute ago, 19.44, and we get z equals 1.49. And from this, we can answer the question with steps 4 and 5 by saying, do not reject, because there is not enough evidence to reject the claim when we take into account that the critical value is plus or minus 1.96, and that z equals 1.94.
When the samples are dependent, as they would in a before or after test using the same subjects, the Wilcoxon signed rank test can be used in place of the t-test for dependent samples. Again, this test does not require the condition of normality, and table K is used to find the critical values. All right. So this example on